to KU Padasala. I am Dr. Syamchand, working as Associate Professor at Department of Chemistry, University College, Trivandrum. In this session, we are discussing the chemistry of nanomaterial, especially the synthesis and characterization of nanomaterials. Moving on to synthesis of nanomaterials. First of all, it should be noted that there are two important strategies for the preparation of nanomaterials. These two strategies include top-down approach and bottom-up approach. First of all, we have to discuss top-down approach. What do you mean by the term top-down approach? In the top-down approach, as the name indicates, we are beginning from a bulk material and now scale down it into nano level entities. That is, nanomaterials are synthesized by breaking down of bulk solids into nano-sized particles. It is based on the principle of dispersion. Preferably, the starting materials are generally in the solid state. Now, the pictorial representation simply gives you an idea about the top-down approach. The left-hand side represents a bulk material. It is scaled down into fragments and finally it is converted to nanoscale materials of desired size. Now, regarding the bottom-up approach, it is an exactly opposite approach of top-down. That is, here nanomaterials are synthesized by assembling atoms or molecules together to get the nanomaterials of desired size. Here, the starting material, the starting substance is either in gaseous state or in liquid state. The pictorial representation gives you a clear idea about the bottom-up approach. Here we are beginning from atoms which are very small entities, allowed to them to combine to get group of atoms or clusters, and the clusters are finally clubbing together to get nanomaterials of desired size. Hence, there are two important synthetic approaches. The first one, we begin from the bulk and scale down to nano. The second one, we begin from the bottom and assemble it to get to the nano. These two approaches are the common approaches for the synthesis of nanomaterials. Now, we can move on to details of the first approach, that is the top-down methods. There are so many top-down methods and these are some important top-down methods. Popular top-down methods include RF plasma method. RF stands for radio frequency. Then thermolysis, mechanical grinding, laser ablation and nanolithography. We can move on to details of each and every methods mentioned here. First of all, RF plasma method. RF stands for radio frequency. It is one of the oldest method for the preparation of nanomaterial, especially applicable to metal nanoparticles or MNPs like gold or silver nanoparticles, etc. And this method involves the vaporization of the bulk material and it is then condensed on a suitable substrate or the surface of a suitable substrate. Metal placed in a container is placed in an evacuated chamber and is heated using high energy radio frequency coils. Picture represents a diagrammatic illustration of the RF plasma method. Here helium gas is used for the injection into the system to form high temperature plasma. The second method, that is nothing but thermolysis. Thermo means heat, lysis means fission, and in this method the decomposition of solids occur at very high temperature. Hence the name thermolysis. It is commonly used for metal nanoparticle preparation. The solid should contain metal cations and molecular ions or metal organic frameworks. Picture represents diagrammatic representation of thermolysis. The material is placed in an evacuated quartz tube and thermolysis happens inside this quartz tube. This tube is further heated to perform decomposition. The obtained nanoparticles finally passivated, made inert by using suitable gas. The third method under top-down approach, that is nothing but the mechanical grinding. Mechanical grinding is otherwise known as attrition or high energy milling. It is a typical top-down procedure. It's a popular method due to simplicity and relatively inexpensive nature of the synthesis. It is used in the synthesis of different type of nanomaterials like oxides, like metal nanoparticles, so on so. Now the pictorial representation of mechanical grinding. Here there are two or more high energy balls made up of stainless steel or any hard material like that, and by rolling that mill in a particular speed, by placing suitable gap between the balls, it is possible to get different sized nanomaterials. This is similar to mill where we are powdering some materials. The mechanical grinding procedure has some important connection with the rotational speed, size and number of balls, the time of milling and the milling atmosphere. All these factors will control the size and quality of the obtained nanomaterials. Nanoparticles produced are by the shear action during the grinding or moving of the high energy balls. Now laser ablation. This is one of the recent and very important method that belongs to top-down category of nanomaterial synthesis. Laser beam is here used as a source of ablation for generating nanoparticles directly from solids. That is, we are using high energy laser beam to convert bulk material to nanoscale particles. Nanoparticles here are produced during the condensation of a plasma formed by the laser ablation of a bulk metal or material. Now pictorial representation of the laser ablation. Here some plasma is generated. High energy laser beam is focused to the substance placed in a suitable container used in the synthesis of stable metal nanoparticles in water or in organic solvents. That is, by the laser ablation procedure, we will get particle dispersed in suitable solvent, whether it may be water or other organic solvents. Now, nanolithography. Probably this is the last method we are discussing under the category of top-down approach. The word nanolithography can be broken up into three parts. The first part, nano, that means dwarf or small particles, and second one, lith. Lith means stone, and graphy, last term graphy. Graphy means writing. Thus nanolithography or simple lithography represents writing onto stone. In general, in nanolithography procedure, we start with a bulk solid and nano-sized patterns are developed on it by removing unwanted parts from the bulk material. There are so many types of nanolithography and some important techniques under nanolithography are electron beam lithography. Simply we can designate it as EBL. Here we are using high energy electrons to perform lithographic procedure. Next one, photolithography. Here we are using light. And finally, nano imprint lithography. There are some other recently discovered methods are also known, and that are far beyond the scope of this discussion. Now, moving on to advantages of top-down approach. Large scale production is possible with the top-down approach. That is, we can prepare enormous quantities of nanomaterials based on the top-down approach. The deposition over a large substrate is possible by this method. Generally, chemical purification of the material obtained is not required. That's a very important advantage of the top-down approach. That's all about the discussion on top-down approach. Now we can move on to the second strategy, that is bottom-up method for the preparation of the nanomaterials. Moving on to popular bottom-up methods. These are very popular bottom-up methods. Nothing but chemical reduction, chemical vapor deposition or CVD, the sol-gel synthesis, hydrothermal synthesis and co-precipitation. These are various methods that we are discussing here. First of all, chemical reduction. Chemical methods are very common method of synthesis of nanomaterials or nanoparticles. Colloidal silver, copper, gold, etc. can be prepared by the reduction of their precursor salt solution. Reducing agents like sodium borohydride or NaBH4 can be used under ice cold conditions to yield nanoparticles of desired size. This is a very popular method of synthesis of nanomaterial. Now, silver nanoparticle can be obtained by the reduction of the precursor salt solution, that is AgNO3, using NaBH4, that is sodium borohydride, under cold condition, or we can perform the reaction in ice. Another example is molybdenum nanoparticle synthesis. We can take molybdenum chloride or MoCl3 as the starting material, perform reduction using a derivative of sodium borohydride, that is sodium triethyl borohydride. By this reaction, MoCl3, here Mo is present in +3 oxidation state, get reduced to molybdenum nanoparticle, where the oxidation state is equal to 0 as per the equation shown here. Now, the second bottom-up method, that is chemical vapor deposition, simply CVD. CVD is a method to produce high purity, high performance solid materials or nanomaterials. This involves the formation of the nanomaterials from the gas phased at elevated temperature. During the process, the substrate, simply designated as wafer, is exposed to one or more volatile precursors which react and decompose on the surface of the substrate. Pictorial representation simply illustrate the chemical vapor deposition procedure. Now, another method belongs to bottom-up approach. It is the sol-gel synthesis. Probably this is a very common method by which we are preparing enormous number of nanoparticles, especially in our common laboratory settings. The sol-gel process is a wet chemical synthesis, wet chemical procedure, that is we are using some solvents for the preparation of colloidal particles. Here, metal alkoxides and metal chlorides are typical precursors for the synthesis. They undergo hydrolysis and polycondensation to form a colloid, that is a system of nanoparticles dispersed in a solvent. The sol evolves then towards formation of an inorganic continuous network containing liquid phase, that is gel. Hence the name sol-gel, sol-gel synthesis. These are the different steps in the sol-gel synthesis. Sol-gel synthesis characterized by the first step, that is formation of stable solution of the precursor. Second step is the gelation step, that is formation of gel. Third step is aging of the gel, it is otherwise known as syneresis. The fourth step is drying of the gel. Then fifth one, dehydration, and the final one, desensification and decomposition of the gel to get nanoparticles of desired size. Pictorial representation of sol-gel synthesis is shown here. We will get a clear-cut idea of the sol-gel synthesis from the pictorial representation shown here. Now, another popular method, that is hydrothermal synthesis. Hydrothermal synthesis needs a special instrument. That special instrument is known as hydrothermal autoclave. Process is at high vapor pressure level and using high temperature aqueous solution. Hence, it is known as hydrothermal synthesis. Hydro for solvent water, thermal for providing high temperature, and hence this method use solvent or water at high temperature, hence the name hydrothermal synthesis. This represents the diagram of a hydrothermal autoclave. Some bursting disc, stainless steel lid, and these are the associated parts of a hydrothermal autoclave. This picture simply designates the inside portion of a hydrothermal autoclave where we are performing the hydrothermal synthesis. Now, another method belongs to bottom-up approach. It is nothing but the co-precipitation method. Here, the required metal cations taken as soluble salt are co-precipitated. Co-precipitated means precipitating together from a common medium, usually as hydroxides, carbonates, oxalates, or as their citrates. The precipitate obtained after drying is heated to a suitable temperature in appropriate atmosphere to produce final nanoparticles. The co-precipitation is a very simple method for the synthesis of nanopowders. Iron oxide nanoparticle can be very easily prepared by the co-precipitation method. Here we are taking two precursor salt solution of iron, preferably in two different oxidation states, that is Fe2 plus, that is ferrous ion, and Fe3 plus, that is ferric ion. They are mixed in 1:2 proportion and base is added, and finally as a result of this reaction, Fe2 plus and Fe3 plus will undergo co-precipitation to produce iron oxide nanocrystals, that is Fe3O4 nanoparticle as shown in this equation. Now, various advantages of bottom-up approach. See, these are important advantages. Ultra-fine nanoparticles can be prepared by using the bottom-up approach. Narrow size distribution, that is we can go to very small nanoparticles, preferably in the range of 1 to 20 nanometer, and the bottom-up approach is comparatively cost-effective procedure. The learners can make a comparison between different bottom-up approach and a top-down approach for the sake of convenience. These two approaches, that is the top-down approach and the bottom-up approach we discussed here, are consolidated in the picture. The left part represents top-down approach and the right part represents bottom-up approach. In the left part, we are beginning from bulk metal and reduced it to nanoscale, and in the right part, we are beginning from very small atoms and clubbed together to produce the desired nanometals. These two are different opposite approaches. One is top-down approach and the other one is bottom-up approach. that all about the synthesis of nanomaterials. Another part of today's discussion is characterization of nanomaterials. You know about the different characterization methods employed for the study of nanomaterials. We can move on to different characterization techniques. Prior to that, what is meant by characterization? Characterization refers to study of materials features such as composition, structure and various physical, electrical, magnetic properties. Why we require characterization? We are dealing with very small particles, that is nanomaterials. The characterization is very, very important, and this is because the properties of the nanoparticles may change significantly with the size and the shape of the nanoparticles. Accurate measurement of nanoparticle size and shape is therefore very much critical to its applications, preferably the biomedical applications. Hence, characterization is very, very important. Now, different methods for characterization of nanomaterials. During the time span of this discussion, we are shortening the different characterization methods and not considering the very minute details of each and every methods. First of all, we can make a generalized idea about different characterization methods. The characterization methods in general can be divided into four categories. They belongs to electron probe methods, scanning probe methods, spectroscopic methods and thermodynamic methods. The first method, electron probe method. This method uses high energy electron beam to find out the structure, to find out the composition, etc. The most familiar methods are scanning electron microscopy, simply designated as SEM, and transmission electron microscopy, denoted as TEM. The diagram represents different important electron probe methods. They include scanning electron microscopy, SEM, transmission electron microscopy, TEM, high resolution transmission electron microscopy, simply designated as HRTEM, which is a modification of TEM, and scanning transmission electron microscopy, that is STEM. Another one, scanning probe methods. In the scanning probe methods, there are two important things in common: a finely sharpened probe tip, a system that enables the scan of the tip over the sample substance under consideration. The image is obtained by moving the probe on the sample in a raster action or pattern. The common scanning probe methods include atomic force microscopy, which is a very popular method, scanning tunneling microscopy, STM, lateral force microscopy, LFM, chemical force microscopy, CFM, and field ion microscopy, FIM. Another characterization procedure, that is spectroscopic method. Spectroscopic methods are also known as photon probe methods. Here we are following photons to probe the structure and composition. Most of these methods involve a primary photon which is entering into the system, that is primary photon in and a secondary photon out. UV visible spectroscopy is the most common method under spectroscopic methods. Common spectroscopic methods are given in the table. The first one, UV visible spectroscopy, used for chemical analysis. Ultraviolet photo emission spectroscopy, UPS, used for surface analysis. photoluminescence spectroscopy to evaluate luminescence properties of the system, atomic absorption spectroscopy for elemental analysis, atomic emission spectroscopy also for elemental analysis. Raman spectroscopy is also belongs to spectroscopic method. It is used for vibrational frequency finding out or vibrational analysis. Fourier transform infrared spectroscopy used it to find out different type of symmetrical and asymmetrical vibrations. X-ray diffraction to evaluate the crystal structure. Energy dispersive X-ray for elemental analysis. X-ray fluorescence or XRF also used for elemental analysis. These are very popular spectroscopic methods used for the characterization of nanomaterials. Now, the last category, that is thermodynamic methods. In thermodynamic methods, we are measuring some thermodynamic properties like mass, free energy change, delta H, etc. Some popular thermodynamic methods are shown here. These include thermogravimetric analysis, denoted as TGA, which is used to find out the mass loss as a function of temperature. Another one, differential thermal analysis. The heat capacity, reaction heat, etc. can be measured by DTA. Differential scanning calorimetry or DSC is another technique. Here we can also measure the reaction heat and phase changes during heating. Nanocalorimetry is another thermodynamic method. Thermoluminescence or TL is a very popular thermodynamic method. Hence, these are very important characterization methods we are employing for the characterization of nanomaterials synthesized. That all about the discussion, and wish you all the best. Thank you.